All right, so today we're going to be talking about the HAL. So what the HAL? What is a HAL? How to use it? A little bit about the Testeract TestPoint HAL, and how using a HAL can be an improvement for a lot of your test automation systems. So a little bit about me. I'm the Testeract HAL architect and a systems engineer at Testeract. I've been here for a little over 2 years. Met Testeract a few years ago at a past job. I have a BS in aerospace engineering from UCLA, and I have about a little over 5 years in the test and automation industry. I've worked in aerospace and defense. I did hardware in the loop, also known as HIL, for a bit. I worked on instrumentation and sensors, and also my first kind of introduction to the test automation world was doing some PLC comm testing, building custom protocols to test that out. So in this presentation, we're going to kind of talk about how the general automated test software stack and how the HAL fits into that, controlling instruments with the HAL, swapping instruments, other advantages of HALs and requirements that may be necessary. We have a demo that we'll show, and then at the end, we'll have a Q&A and discussion. Feel free to ask questions at any time in the chat, and we will address them at the end. So let's take a look first at the test automation software stack. We have these 4 components here. We have acquire, analyze, present, and govern. The scope of this presentation, we're mostly going to be discussing the acquire part, which acquisition is actually talking to hardware using specific protocols and buses to communicate with the instruments. And then we take measurements, that is the analyze part. We apply limits, check for pass fail on those, and kind of basically say, does the data that we're reading match what we expect it to? Then the next portion after that in the stack is presenting it. This could be through a manual UI or actually like printing it out to a report, saving it to a database, maybe doing diagnostics or logging to see what's going on. And then governing, that's kind of the top layer of the stack. It more has to do with processes and workflow and how we kind of establish these to, have an effective test automation system and high reusability and basically take advantage of HALs and other parts of the framework. So let's look at a simple example. If you're familiar with LabVIEW, you've probably seen something like this before. We have an instrument, it's referenced with a Visa handle, and we'll open that Visa session. We'll do a Visa read, that's our acquisition part. We're actually reading instrument or data from the instrument. We'll close that Visa reference, and then we'll take that data out, apply it to some sort of limit checking. In this case, we're checking if the value is 0.5, and we'll see if that passed. So this is a very simple example. As you can see, it's very specific for one case. It's not scalable. And really, can't be reused. It's just for one very specific test. So this is a simple example. It'll work for one case, but it may not be best for kind of an extensible or modular solution, which is what a HAL can provide. So what exactly is a HAL? A HAL, it stands for hardware abstraction layer. And as you can see over to the right, you can see where it kind of sits in the stack. It's the bottom of your software stack directly interfacing with that hardware. So the point of a HAL, as the name suggests, it abstracts the user from these low-level communication details with the hardware. You don't need to know, if you are a developer just kind of using the HAL, really what is going on underneath. One person writes it, 2 people write it, they know what's going on, and the rest can use it. It's all abstracted. You just have to assume it's a black box and it's going to work. And this kind of encapsulates that information needed to interface with this instrument. So this, in effect, decouples it from the software stack. So each device is responsible for its own data and only its own data, which is very powerful because it can live in kind of this environment where, it does its thing and passes that data to and from up into the stack or down, receives it down from the upper parts of the stack. And we have an API that kind of provides an easy access for controlling the state, calling to these instruments, and accessing it from other parts of the stack. So looking how this fits into the general TestPoint framework, we can see here that the HAL is kind of the bottom part, and this is the rest of the stack. This would be your analyze, present, and govern parts of it. And the hardware abstraction layer directly interfaces with the test hardware and also with the device under test, also known as the DUT or the unit under test, UUT. So this is just kind of where it fits into the picture. It's really that bottom layer that, fits the whole kind of system together. So the main goal of a HAL, or at least what it should be, is that you should maximize reuse. Writing hardware interfacing code, driver level code, whatever you want to call it, is often costly, expensive, and time consuming because you have to figure out a lot of low level details. You may have to work through certain issues with the instruments that may not be apparent. So, kind of having a part that you can reuse and swap in and out is really powerful because that's where a lot of your development time comes from. And as we can see in this picture, the acquire part is the only thing that's going to change, but the rest of the stack really doesn't need to change. And that's kind of the power of a good hardware abstraction layer. It should kind of be model independent, where the model that you're using doesn't really matter, and you can kind of swap the interface in, and you can swap the instruments in and out without changing your interface to the rest of the software stack. So we looked at our simple HAL example. Let's say we improved it just a little bit. So say we added a VI, a method sub function in here where the acquire is pointing to called get volts, and this would retrieve the voltage from a power supply. As you can see here, we have kind of like stacked case structures with a bunch of different instrument names in there, and it would call the correct driver for that. So this is better, than the first example that we had because we can expand it to handle, more instruments, but there are some problems with this. So every time that you do, change this, you're going to have to update your API, which could flow in a breaking change up in your software stack where, things are broken, you'll have to recompile them, which can be quite a pain. Especially when you're working in an environment with, high quality control and, you need to revalidate certain parts of your test station before maybe testing it on hardware. So that's what leads to regression testing. And also with this example, you're kind of limited to only Visa connections. What if you had an instrument that was GPIB or serial or IVI? It wouldn't really work in this case. You'd have to do a lot of work to kind of expand that. So this just isn't really a great scalable solution for a HAL. It is better than the first one, but it's not really what we want. So how do we solve those? We solve it with object-oriented and dynamic dispatch. So dynamic dispatching is where it knows basically which instance of that class it's going to evaluate to at runtime, which becomes really powerful because you essentially swap in and out different models, whether it's a Keysight 6700, a simulation power supply, or one using the NI DC power drivers. So we can have basically a model independent API where, if you need to swap instruments, you don't need to touch that API. That API doesn't care what it's actually calling, it'll figure it out. But from the software stack, it just knows I'm going to call this API and I know it will evaluate to the correct instance and implementation at runtime. So every time we add an instrument, we don't need to rebuild. We just have that API. We'll just only have to build the model specific interface code. And this kind of saves us from having to do that regression testing. We only need to test the model code that we updated or added. We don't have to test anything else in the software stack because the software stack doesn't care what's going on. And this is also really powerful because we can add additional buses and protocols. We can, have it so that it's set up, specific for each model that you are using. You're not limited to just Visa. You can use, again, any of those other types of buses or protocols that I mentioned. So you may be asking yourself, do I need a HAL? There's pros and cons, of course. But in general, the pros definitely outweigh the cons. So, without it, new instruments are really hard to add. So this kind of adds tech debt to your stack. If you're kind of in an industry or a company that, is often doing this, just because you do it once, you may have to do it in the future. You may have to build up a new test system. You may have to rev up to, get better models, or maybe ones become deprecated. So, kind of sticking yourself with just one model or type of instrument can be a pain because it may kind of hurt you down the line. And also, having a HAL helps because you can parallelize the development. Everything in a well-designed HAL should be pretty modular and individual packages that kind of link together at runtime. So you can kind of parallelize this development among your developers and help speed up your time to completion for your project. And again, as I mentioned, this protects against obsolescence because, you can easily add new instruments. As again, maybe one comes out of date, maybe the model you selected for your instrument, isn't up to spec, or you need, a higher performance one in the future to test certain things that may come up. So with having a well-designed HAL, you can essentially fix this and, protect against that obsolescence. Yes, there are cons to a HAL. Of course, it is a higher upfront development cost, but in most cases, you will get a high return on investment if you design it well and use it properly. Another statement, and I hear this a lot from, various customers and stuff, is I'm only developing for one set of hardware. Yes, that may be for some cases, but it's a very small percentage of cases. And things may change down the line. So if this truly is a one-off thing, maybe it's just a quick prototype. Yeah, you don't need to build out a full HAL. But if you are, having a professional automated test system, you're, trying to validate or test, deliverable hardware, this may not be the case, and things may expand down the line. Again, another thing I hear, that require hardware will never change. Yeah, it might, but in most cases it will. So you kind of need this flexible and, extensible solution to help with that. So potential HAL features and requirements. These are some things that, you may be thinking of. Everyone will have, different requirements for their system, depending on, what they're doing, what they need to accomplish. So these are some features of the Testeract TestPoint HAL that are really powerful. So we're going to go through them. The first one is swapping, and I think this is probably the coolest thing about the Testeract TestPoint HAL. We're able to swap instruments without touching that code. As I mentioned, a well-designed HAL should have a model-independent API where you can easily swap in and out instruments without affecting the rest of your software stack. So this is really powerful if for some reason you need to send, a model out for cal. You need to put in a new one temporarily while that one is out for cal before it comes back. Maybe again, you found that the instrument you selected isn't as high performance as you thought, and you need to swap it out. So being able to do that on the fly very easily is really powerful because the rest of your code doesn't change. Just a few lines in a config file and you'll be on your way. Another thing is it should be able to support any device, and device does include UUT or DUT communication. So really a HAL should be able to work with any bus, instrument, or connection without really affecting anything else. So kind of all the details of connecting to that, writing to it, can be abstracted and all encapsulated inside your specific class or object of your device that you've selected. Another really important feature that I think almost every HAL should have is simulation. A lot of times when you're developing, you are not with the actual test hardware. It may be in another state, it may be in another country. So being able to kind of simulate the behavior of a specific instrument really can help squash a lot of bugs and get kind of your system really far along before you even get to that integration stage, which is usually the most time-consuming and difficult part of working with instrumentation. So being able to have that simulation, being able to take care of that all up front really, really helps and can really cut down on the most time-consuming and difficult part of your entire development process. Another key feature is logging. A lot of times customers will want to know, what is the actual instrumentation doing? What is it reading? What is it writing to it? Being able to log all this is really powerful because you can, have that information and easily turn it on or off. Another thing is when things go wrong, you can easily turn on logging and kind of have basically things that you can read to figure out what is going on, what is my application doing that may not be incorrect. So it helps cut down on your debugging time. And really you want to do this without impacting the execution speed. So the Testeract TestPoint HAL has logging automatically built in, and that is an asynchronous process that is handling those logs. The HAL simply just ships off that information to that asynchronous process and handles where it's being written to. And we'll see that a little bit later in the demo. Another thing that most HAL should have is tools that allow you to easily develop in the HAL, which may be like project templates. Another thing is debug tools. We have a great tool here, which again, we will show a little bit later in the demo, which is the HAL debug tool. This allows you to basically expose the individual methods or functions inside your API and kind of run those, inside your system to figure out what's going on if an anomaly were to occur. And with the way the Testeract TestPoint HAL is built, all that can share the same application space, so you can actually pause an execution of a script or your GUI or something, and then open up this HAL debug tool and basically be able to evaluate the system in the state that it is in, which becomes really powerful because you don't have to kind of shut everything down. You can really figure out what's going on in the moment. Another really cool feature, which we'll show again later in the demo, of the Testeract TestPoint HAL is the record and playback. This basically allows an operator to come in and run individual HAL methods and then record and play back them later. They could export it to a test stand sequence file, to a CSV file. And this really helps, if you have difficult routines with certain instrumentation that you're trying to capture before, you actually get it into an automated test. This allows you to kind of play with that and form these little, basically sub functions of, setting up and acquiring from the instrument. Another really powerful feature that most HAL should be able to handle is shared connections. So a lot of times instruments, you may need to alias certain components of that instrument. Maybe it's an instrument supports 2 or 3 channels, and you need to all use them individually. Well, in a lot of cases, you may run into visa or instrumentation clashing where you're trying to write to the same instrument at the time. If you have a HAL that's well built, which can handle these shared connections, you're not going to run into that. It's only going to make sure that it's talking to the instrument one at a time when they share that kind of same connection. So this becomes really powerful and can kind of lead to preventing, some synchronization and race conditions that you may have to account for yourself. So if it's all built into your HAL, the developer doesn't have to worry about that. They can just assume and know that it's going to work correctly. Last part is, I touched on this briefly, a really powerful feature of a HAL is you should be able to abstract most of your UUT communication within the HAL. Most UUT communication is very specific and custom. You don't want to have your developers, if you're trying to write a bunch of scripts, say you need to write 100+ scripts to test one UUT. You don't want them to have to worry about sending specific data or making sure bytes are aligned correctly when you're trying to write to a UUT. You can just abstract that all in there. They can call the API and be on their way. And, this just really helps with, development. You don't need everyone to have the specific information. They just need to know, I'll call this and it'll do what it needs to do with our UUT. So looking at a HAL overview, this is an example of kind of how the Testeract TestPoint HAL is set up. So right here up at the top is our main important driver of this, which is the device manager. This is basically another asynchronous process that's always running in the background. When you first call the HAL, it boots up automatically and shuts down at the end automatically. And this kind of holds your devices in all the state of your system and the state information of that device. So when you call a specific device, the device manager will, retrieve that in the state that it was left in. And also the HAL manager or device manager will essentially handle kind of all your shared connections, synchronization, preventing any race conditions. So really it does all the heavy lifting. It constructs your objects, it destroys them at the end. And it really just kind of takes care of all the nuances of the HAL without the user having to think about it. So right below that, we have the device. And a device is basically an abstract ancestor class of any single class that you're going to have in your HAL. So one benefit of this is, you have a single thing that all devices inherit functionality from. And you can basically reuse a lot of components from that, like loading data from a config file, which in the Testeract HAL, we have, configuration files called our device config files, which are automatically read in when you construct your device. And this allows you to define certain keys that will be loaded in at runtime to kind of configure your instrument the way it needs to be. So having, a single ancestor class that can kind of handle all this functionality, again, abstracts the user from a lot of having to do that themselves when they're writing a HAL. So there's even benefits, to this when you are developing, because you don't have to worry about, is the data going to be loaded in properly? You'll just know that it will, come in. So all classes in the Testeract HAL, inherit from this device, and this is a good approach because you can reuse that functionality. So moving down another layer is this API layer that I talked about. So you basically define what's called a device type, and a device type is a family of instruments. It might be power supplies, analog inputs. You may have a UUT, could be an RF signal generator, DMM. You get the idea. It's a specific type of instrument, that does certain things. And really, this works out because, for example, most power supplies have similar functionalities. You want to set your voltage, set your protection levels, enable your output, shut off your output, maybe query what the state of the power supply is, what voltage and current it's outputting. So you can kind of define these API methods that are very general for each power supply. But since power supplies all kind of work the same way, this works. You can just call get voltage and it will return the voltage that's being output at the time. So this is what's called from the rest of your software stack. And, the way the Testeract HAL is set up, that we call an API that's model independent. You simply just specify your device name. And at runtime, it will dynamically dispatch the next layer below in the stack, in the HAL, rather, is the model class. And these are specific implementations for specific models. So we can see the example here. We have a Keysight 6700, a simulation, or a Sorensen power supply. We can kind of abstract basically all our connections, anything that's needed to connect to it, maybe any protocols or buses that are included in there. And then also the driver level interface codes, Skippy commands, whatever you're using to actually write and read from the instrument, that is all contained and included inside your model class. So again, based on which device name that you specify to the API, this will automatically, look in the HAL device manager and dynamically dispatch, the specific model that you're using. And this works because, all models inherit from an abstract power supply class. So they all share the same methods. They're all defined the same inputs and outputs, simply just the core, the details, the meat and potatoes, if you will, of the model actually, execute at runtime. So this is kind of how everything works inside the TestPoint HAL. And this is also how, we're able to have this abstraction with an API and not really concern the low-level details if you're a developer. So a little bit about deployment, having kind of this piecewise modular approach becomes really powerful for deployment, because you can basically have libraries, which we see over here on the left, that you can kind of pull in to what are called feeds or solutions, basically the lists of packages that you're going to install on your system. So you simply can just come in, select, just the packages and things that you need. Maybe you just need a DMM and a power supply and then 2 models for each. Great, just pull all that information in along with the HAL core and then some other tools and stuff, maybe some GUIs. You build a solution, you build a state or a snapshot, and then you install that on your machine. So this becomes really powerful if you have a bunch of stations. I've had certain customers where, we're setting up 4 stations. Great. We get one working, we build a state, and then they can expand it to infinite stations simply by just clicking a button and installing all those packages onto the machine. So let's kind of look at an example of, using the Testeract TestPoint HAL and also, other parts of the framework with testing in actual products. So maybe we're a flashlight company and we're making a bunch of flashlights, and we need to, the first model we come out with, it's a very simple flashlight. So we have a photometer and a power supply. The power supply is, hooked up to the flashlight. We're going to read our current and voltage on it to make sure that's pulling the correct, current from the power supply. And we also have a photometer because we need to make sure, does the flashlight work? Is it producing the, light that we need it to? So if we see here on the left, we have the HAL, and, we'd have the HAL core and a DC power supply. And say we already had a DC power supply used on another project and we're using the exact same model, we can simply just pull in those packages, reuse all that code without having to think about it. And in this case, we just build up a photometer HAL class where we have our specific photometer that we're using for this test system, and we get that model working. We build it into the HAL. Great, it's up and running. And then we have task, which you'll see task a little bit later in the demo. Task is kind of our all-encompassing GUI solution where we can have a bunch of GUIs that we can flip through. So maybe you have a requirement that the operator needs to be able to do some things manually. So we build up a photometer kind of GUI used to control this. And we can also then pull in kind of all our other packages that we have that will run in task. We have a test stand executor, our HAL debug GUI, a logger console, and maybe we already have a DC power supply GUI already written from a past project. So we can just pull all that in, and we don't need to do all that. We just need to write the new photometer one. And then inside test stand, we will have specific files to run these tests. So the first one that you'll kind of see up in the right of the test stand box is the client file. And a client file is basically your entry point, or what should be your entry point to kind of any automated test. And client files are usually specific to each station. So we'll build one that's specific for this flashlight tester station where it allows us to, select the test that we're going to run, the UUT. We can basically input information for like the serial number and everything, and maybe select certain conditions about the environment that we want it to run in, and then we can click go. And the client file will then in turn call a TAL, which stands for test abstraction layer. And the test abstraction layer is simply a routine for a specific UUT or a specific test of a UUT. So in this case, we have a TAL that is, going to run through and have all the information and limits and, everything we may define the requirements for testing this simple flashlight. And the TAL in turn will call certain routines called TMLs, test module library, which test module library sequences do very specific routines. So here we have an example of a current draw test where we will have a routine that, talks to the power supply, calls those APIs from the Testeract HAL and performs the current draw test, reports that information back up to the TAL where the TAL will evaluate those limits. Same thing with a light test. We can just build a reusable routine, which will, test the output of the flashlight, report back values, and then our TAL defines what those values should be to have a passing condition. So this is a very simple example with just one DUT. What if we added a new DUT? We have a new flashlight. It's, a little bit, has different, requirements, maybe different limits that we're checking against. We expect it to have maybe more of a light output and to draw a certain amount of current that's different from the other flashlight. Well, great. We just only need to add a new TAL file. We can reuse everything else in our stack from the HAL up through the TMLs in the client file. We simply just need to add a new TAL file because we can reuse the same TML routines for the current draw and the light test. We simply just need to kind of define our requirements or our passing conditions for this new flashlight, and in turn, just call that TAL. So with adding a whole new flashlight, we barely have to touch anything in the stack, just the very specific components that are needed to test that. So what if we, for some reason, needed to add a new test? Maybe R&D came back and said, we need to test the sweep, or we need to sweep basically over certain voltages to see how the flashlight responds. Maybe if the batteries were dying or something. So all we have to do is simply add, a new TML sweep sequence where it will implement the sweep test, and then we just flow it into our TALs and call it a day. We'll add conditions that are specific for each model of our UUT, and then we'll be on our way. So again, adding a whole new test, very little needs to actually be done. So another example, what if we had a more advanced flashlight, and we have a tri-state flashlight here, which may use an I2C bus. So what we do here in the HAL is the I2C bus, we call it part of the UUT communication. Essentially, we can build a tri-state flashlight, HAL class where we abstract all that I2C specific protocol information inside this HAL class. And we know that we can just call the UUT class and it will do everything we need it to do. And then from there, we'll go and we'll build a new TAL file for it. We'll have a tri-state flashlight TAL, which may run the current draw light and sweep test, but also we need to test the tri-state specific functionality of it. So we'll add a new TML that'll only be called by the tri-state flashlight called tri-state light, which basically calls into the UUT HAL and executes, all that functionality and tests out that I2C bus or whatever other communication you may need with your UUT. So again, we're seeing here that we can abstract kind of these low-level protocol details inside, the HAL, and then simply just call that from a TML, from a TAL, from test stand, from task, whatever it may be, without having to expose the developers working on that to these low-level details. So let's take another example. Maybe we need to figure out, how does this flashlight behave in different temperatures? So we set up a whole new station and that's connected to a temp chamber, and we need some way to control that temp chamber. So we build up a HAL that will interface and control that temp chamber. And then, since it's a whole different station, we'll add a new client file, which is specific for this station that's controlling the temp chamber. So maybe we added, inputs for the temperature. Maybe we have a path to a file that shows, it's basically a giant list of times and temperatures, and it'll basically format your thermal cycling to run that. Whatever it may be, we'll create a new client file that will, take care of all setting up that chamber and running that chamber. Maybe it's an asynchronous process, whatever it may be in your design. But those are the only two things that we need to add, because we can just call all those same TALs because we're checking those same conditions, under thermal cycling. So none of the TALs need to change. None of the TMLs need to change. The rest of the HAL doesn't need to change. We simply just need to add the functionality to control that temp chamber, and then also to set those settings and run it from test stand. So I'm going to turn it back over to Jason here. We have a demo that was pre-recorded showing kind of all these things. First, we'll talk about configuring instruments. We'll show how the HAL is used from LabVIEW, showing it in task, and then also looking at logging in that record and playback that I mentioned. So now we will be doing a demo showing how to use the Testeract HAL. We will start by configuring some instruments. Then I will show how to call that from LabVIEW using our API. Then we will open up Task, our all-encompassing GUI solution, and show you how we can call it from the runtime and use some GUIs that are already pre-built. And then we will also show off logging and record and playback. So let's first open up the Testeract configuration editor. This will launch, and we will go to the HAL devices tab right here. And we'll first click this plus to select to add a new device. We'll select DC power supply, and we're going to change it to the simulation because I'm not connected to any hardware. We'll hit create. And we can see over here on the right-hand side, we have a bunch of keys, the device type telling it that it's a DC power supply. And that's device class is a DC power supply simulation. If we click this plus, we can see a bunch of other available keys. Some of these are DC power supply specific, like channel and voltage noise. Some are inherited from device, like cal expiration, time and date, or the connection alias, which is used to connect to Visa or TCP or any other bus or protocol that you're using to actually communicate with the instrument. So this is just a simulation device. We're going to leave this be. But I could come in here and I could select the Keysight N6700 model class, and we can see that some other keys have appeared here, like the channel, connection alias, and share connection ID, because those are required for that model. We're going to come back here and we're going to change this back to simulation, since that's all we need for now. And we're also going to do the same with a DMM and an RF signal generator. So now we have our three devices. These are the aliases and how they will be called using the Testeract API, DCPS, DMM, and RFSG. So let's go ahead and close this up and let's launch LabVIEW. So we'll open up a new VI and I'll right click to open the quick drop palette. We will go to HAL and then DC power supply, and we can see we have all our methods for the DC power supply that are available to us through the API. Let's start by throwing down an initialize. Then we will come over here and we will set the output voltage. And then we will set the output state to turn it on. And we're going to duplicate this because we're going to turn it off at the end. And then we will grab a get function to get the output volts actual. And finally, we will drop down a closed function call. And let's go ahead and wire these all up. Let's create a control for this where we'll put in our device name, which will be DCPS, and just wire this into all of our APIs. And then we will set the output volts. We'll just do a constant 5 volts. We will set the output state to on. That's done with true to enable it. We'll do an indicator here so we can see what we're reading back. And we'll set another constant false to turn off the power supply. So let's just clean this up a bit and let's go to our front panel. Let's also throw out an error indicator. And we'll come in here and we will put DCPS and we will run this and see what happens. So running this, we see 5 volts out. That's because this is a smart simulation device where we've actually implemented to mimic the behavior of an actual power supply in the simulation class, so that you can kind of make your programs behave in the development environment like they would when they're running in an actual production or deployment environment with the real hardware. Run this a few more times. We'll see we're getting a little bit of noise here. We have that built in where sometimes it's going to make it a little under what was set to just kind of mimic the real behavior of a power supply. And that's how you call the Testeract HAL API from LabVIEW. So you could build this into a PPL, create a big GUI for an operator to use, or you could just build routines and stuff out of this and then compile it and call it from test stand. So we're going to shut all this down and let's actually go into the runtime environment. So we're going to come here to task and launch that. And we can see here we have a bunch of modes here on the side. And this is one to control the DC power supply, one to control a DMM, a log console to show any calls that are being written to the HAL, and replay, which we'll show at the end. So this is our HAL debug. If you come inside here, you can select all your devices that are available to you. You can see they're the same aliases that we defined in the beginning. We'll come here to DMM, and we can see all our different function calls here. So we can select any method, maybe set DMM function. We'll set it to DC volts. We'll hit run VI, and we can see that we are initialized. We come here to get DC function. We get DMM function. We see we get DC volts. I could come back here and set this to something else. Maybe we're in 4-wire resistance mode. We'll run this. Run it again. See, we have changed to 4-wire resistance mode. This is also a smart simulation device to be able to mimic the real behavior of a DMM. We could also come here to the DMM task mode. We could select our DMM from here. You can see it automatically pulls in that we're using 4-wire resistance. We could come here and change our absolute resolution and our manual range and our DMM function. So let's change it back to DC volts. Let's change the absolute resolution. Let's just make our range 10. We'll hit set, and that sets our config. And we could come here to the HAL debug, since this is all in the same application space. We can come back here and read all this information. So you can see our absolute resolution is exactly what we set. You can see this goes back to DC volts. We get our range, we can see our range is 10. So this is all sharing the same device under the hood. It's all managed by the manager, but since it's the same application space, it's the same process and the same copy of the device in memory. So this is really powerful because you could run scripts or do things manually. And if something happens, an anomaly occurs, you could pause your execution, come into this HAL debug, select different commands and do some low-level debugging and try to figure out what's going on. So just playing around here, we could get our status. This is all just simulated. It's just going to print out a bunch of random data here to kind of mimic a DMM measuring. This is all simulated fake data, so it doesn't really mean anything, but just showing that. And if we come here to our log console, you can see all of our calls have been logged here with all the info. So we can expand this one way or the other. Let's expand it this way to show the table view. You can see which log level it is, ranging in severity, our timestamp of when it was executed, which device it is, the class, the library that the API is from, the method that we're calling. You can see we have a bunch of read single measurements from that chart, and then also where we set all our different things, and this is logging from everywhere. So if we did it in the mode or the HAL debug, it's all going to get logged to here. And then we have our different IOs, so our inputs and outputs. So this gives the name and then the value that we set for it. So you can see all this here. If you go to our text view, you can see the exact same information, just formatted a little differently into a text log. So let's go ahead and clear all that. And let's close our DMM. And let's go to replay. So replay now allows us to basically start a recording, execute a bunch of different HAL functions, and then be able to play and record that and then play it back. We could export it to a teststand sequence, run it from teststand. But let's just go ahead and show this off. So we'll go here to new. This will create a new recorder file for us. We'll go to record and we will hit start. We can come here to our HAL debug. Same thing, we'll initialize our DMM. We could reset it. We can configure our DMM function. Let's again set that back to DC volts. Let's set our absolute resolution to 0.01 volts. And let's read some measurements. So we'll read a few measurements here. Then we could also go to the RF signal generator. Let's initialize this device. And then we can set some different settings on here. So we'll go to configure RF. We'll set our frequency to 9 gigahertz, and we'll set our power level to 5 dBm. We'll run this, and then let's configure the RF mode. We'll set it to CW. And then let's configure our output state. So we'll go to configure output state. We'll turn this on. We'll wait a little bit. We'll turn this off. And then let's go to our DC power supply mode. We'll initialize our DC power supply. We'll set our voltage to 5 volts. We'll set our over voltage to 7, our under voltage to 2, and we'll enable the output. Wait a little bit. Turn it off. We come back here to replay. We can pause our recording, and we see every single call that we have made to all our different devices in the order with wait times in between. Now these waits are kind of long because I was doing this all manually. Maybe we necessarily don't want that. So we can come back here to the editor. Let's stop this. We'll come to the editor. We could select all these and let's just set it all to a ½ second wait. So now these are all ½ second. It will take a ½ second in between executing all these different methods. We can come back here to the log console. We see that all that has been recorded. Go back to the default view and let's clear this to show this running in action. And we'll go to playback and we'll hit start. And this is going to run through and we can see all our different functions being called from the HAL with the exact values that we put in and playback complete. So the last part we just have is a Q&A. So monitoring the chat, feel free to ask any questions that you may have.
So I have a question. So before you worked with the Testeract HAL, had you worked with other HALs before?
Yes, very rudimentary HALs. They were very very hard to use, very a lot more embedded into your software stack. So again, they were more kind of like that second simple case that I showed in that presentation, where they didn't really use like a dynamic dispatch at runtime. They were kind of just like adding to it over time. So it was scalable to a point, but not really what you want. So when I first was exposed to the Testeract HAL, I was working for a customer that ended up being a client of Testeract's. I remember one day, we were running a test and we realized that the RF signal generator that we were using was not up to spec that we needed. So I had written these kind of scripts using the Testeract HAL, and you know, they were running, everything was working, just we weren't really getting the right results because they weren't, you know, high precision signal generators that we needed. So I remember that I had this all written and working, and I was like, oh no, they got to swap this out. But then I just remembered, oh, I just need to change a line in the config file because the Testeract HAL is, you know, model independent. And I specifically remember about this. It took me more time to actually hook up the hardware to the test rack to pull it out, stick a new one back in and hook it all up and set up the connection than it was to actually like change the instrument in the HAL. Changing that in the HAL took about 5 seconds, and we were up and running in under an hour. So, you know, that was kind of when it clicked for me. I was like, this is a really awesome framework. And, you know, I saw the power of this kind of design that allows you to act like this. And I see we have a question.
We have a question.
Yep. So how do the changes made in that demo, for example, setting the RF or power supply parameters, correlate to changes in a test stand sequence file? What do you mean by that exactly? Like if you were changing kind of your inputs to that, or I guess I'm just trying to get a little bit of clarification. I'm used to seeing those changes made in test stand. I'm curious if these are completely different workflows. So yeah, they're kind of different workflows. Typically, you know, in at least the Testeract framework that we kind of use for test stand, we have our routines, you know, that I talked about, those TMLs that kind of, you know, run specific sequences or like groups of, you know, calls to the instrument. And typically we'll just pass in parameters. So maybe you'll take in like, you know, a frequent, if you're doing one for a signal generator where you just have to like turn on a signal generator or something, you'll take in parameters for, you know, the power level, the frequency, maybe how long it's going to be on for or something. Maybe you have a weight in there. And then maybe you'll take some sort of measurement and pass that back up. Typically, we all define that on kind of the TAL level, whether you have kind of just inputs that are hard-coded, maybe they come from a property loader file that's like loaded in at runtime that operators can change without actually having to change your sequence. So like doing all that, usually you'll define your parameters inside your TAL level, you'll pass it down to the reusable TML sequences, and then they'll pass data back up, which will then be evaluated. So I hope that answers your question. That's what I think you're asking.
Any other questions out there before we get done? Well, if there's not any questions, so you could
Josh has one last question.
Oh, well, yeah, it does have one last question.
Does a Testeract HAL user interact with teststand the same way I have traditionally used teststand? It kind of depends. You know, you can, you know, flow in our API, you know, in the normal teststand IDE and run it straight from there. We also have like a teststand mode for task, which, you know, we have in task and you can run scripts from there. You'll basically point it to a client file, which will, you know, run it at first and kick it.
Oh, you froze.
It all application space. So task is going to kind of share that whole application space to be able to save that state. If you're running it in, you know, just the teststand IDE, your normal environment that you're used to, and then you have like another GUI or something open, they're not going to be in the same application space, and you're going to have two copies of your device in memory. So it kind of depends. If you're simply just running test stand sequences, you can call the Testeract HAL the same exact way you've been doing it this whole time. If you have other kind of GUIs that are running at the same time, you need to do something that syncs up your application spaces so that test stand is sharing that, whether it's calling your test stand sequence from that LabVIEW GUI somehow, which is totally doable, or if you're using some sort of like test stand custom UI that you have built into another application like we do in Task. So effectively, from a developer standpoint, it's the same exact way you're used to calling like LabVIEW and running LabVIEW from test stand. It's just kind of the way, if you have other applications, that you need to be conscious of that application space to make sure you're not, duplicating instances of that object or that device in memory. You're welcome.
Cool. Well, I think we're actually about out of time anyway, so this was great. Thanks, Tom, again for coming and presenting on this. This is really good. If anybody wants to see Tom in person, if anyone's going to NI Connect, you can go and see him there. He's going to be presenting there as well. I will also be there at NI Connect. And next month, we're going to be probably following up this webinar with another webinar where we give a little more practical kind of my experience in using the HAL as a newbie. So that should be interesting for next month. So once again, thanks everyone for coming and have a great day.
Thanks, everyone.